Okay, we're recording. So, we're going to do all of Chapter 4 today. 3 sections of Chapter 4. Good news, we don't have to cover every single little bit of it, and a lot of it is really fast, and a lot of it is highly analogous to single variable optimization that y'all have already seen. So I think a lot of this will go quickly. I think it's very reasonable we can get this done in a single 75-minute lecture. So here we go. Section 4.1. This is a quickie. There's a bunch of stuff in section 4.1. Again, y'all have already seen. I'm not going to spend class time on single variable Taylor polynomials. That's in the prerequisite trail for this course. So make sure that you know about Taylor polynomials. Here, for example, is the Taylor polynomial of degree k for a function, some appropriately nice function at some point A in its domain. And the reason I bring this up, though, is I want to point out what is the defining characteristic of this as what makes this the Taylor polynomial of degree k. And the answer is that this is the unique polynomial of degree k that I'm going to say mimics the function. And what I mean by that is it agrees with f in value, in derivative, in second derivative, third derivative, fourth derivative, etc., all the way up to and including kth derivative at the point A. So this is what I mean by mimics. It's copycatting. I mean, at the point A, it's doing everything that a copycat of f possibly could at that point A. So there is always going to be exactly one polynomial of degree k that satisfies these constraints. Okay, so with that said, we can take this idea and generalize it to a multivariable setting. We can say, all right, for a multivariable function, let's talk about the unique polynomial of degree k that mimics the function that we're approximating. Again, up to kth order derivatives at the point in question. And the only sort of extra little detail is, there's not just derivatives, there's partial derivatives, right? So, for example, when I say p mimics f in value, okay, fine, yeah, sure, the function only has a single value. But in terms of first derivatives, there's actually several first derivatives that p has to mimic f. Right? And then, again, even more second partials, even more third partials, and all the way out to, and including all of the kth order partials. Right? So all this is just kind of, like I say, copycatting what we did in single variable. We're just mimicking the function in terms of values and derivatives as much as we possibly can. That's all a Taylor polynomial is. With that in mind, then there's the question of what exactly is the function that does all of this, right? How do I mimic that function? And turns out you can just kind of write down a formula. And the formula does get a little bit unwieldy and clunky. And all we're going to worry about in this class is the second degree Taylor polynomial for a given function. Just up to second degree, that's it. And it's actually pretty believable. As follows. So you'll even recognize the first two terms as being the linear approximation. Well, yeah, of course it is. Right? That's a convenient fact in single variable calculus as well. The first order Taylor polynomial is the linear approximation. So old news. And then there's really just the one remaining question is, what is the second order term? And this is a kind of a trial and error observation, really. But here's the formula. It's this thing right here where there's a matrix called the Hessian matrix with which you generate this quadratic form. And there's a term that y'all might have thought you'd seen for the last time in linear algebra, and yet here we are. Quadratic form is fundamentally what that second order term is. So, So anyway, there it is. Now, it's an exercise to confirm that this has the appropriate partials that it's supposed to have. And again, that's just a matter of tedium. It's just a matter of kind of writing down all the terms and taking their partials, just confirming that they are what they're supposed to be. Okay, so that's a nice exercise that y'all can do for yourselves. Okay. Do notice that this matrix is very conveniently arranged. It's got this sort of nice property that in the first column, for example, we're taking one of the partials with respect to x1. Likewise, second column, likewise, third column. And then notice in the first row, the other of the partials is with respect to x1. So it's got this kind of, orderliness about it for convenience. Okay. All right. That's all we're going to say about section 4.1. Everything else is either review or I think pretty straightforward. Okay. Moving along. Section 4.2. We're making great time. Okay, so section 4.2, again, let me remind you about single variable calculus, right? So in single variable calculus, we make the following argument. Let me rephrase that. The following argument is implicit in single variable optimization. All too often it doesn't get said, right? All too often students get told kind of half-truths, which is, things like, if the derivative is 0, then you have either a maximum or a minimum. That's not true. It also doesn't follow. It's a sloppy statement. So let me show you what is underneath it all in single variable optimization that's actually happening that will result in an actually valid statement. So if you make certain assumptions about a single variable function, right? So if we suppose that we have a point x that's in the interior of our interval. Notice it's not one of the endpoints, but it's well inside in the interior of the domain there. If we assume that the function is differentiable, I don't know how to draw that, but so let's assume that it's nice and regular there, right? So we need, in fact, all we need is differentiability. And specifically, if we assume that the derivative is non-zero, that didn't come out well. The derivative is non-zero. In other words, that looking as we are at a graph, that the slope of that tangent line is non-zero. That couldn't possibly be a maximizer. There's no way. How could this point conceivably be the maximizer? How could that be the point where f is as big as it could possibly be? Look at this. The function is actively in the process of getting bigger. Right there. It's currently increasing. If it is still increasing, it's not as big as it could possibly be. Right? That makes sense? Okay. You might say, hey, what if the derivative's negative? Then the function's not increasing. Well, it's not increasing as you increase x, but it is increasing as you decrease x. Right? There's no law that says we have to approach the maximum from the left, right? How we could conceivably approach the max from the right while going to the left. Point is, if the derivative is non-zero, one way or the other, the function is increasing, and therefore this could not possibly be the point that we're looking for. So that is definitely not a maximizer. That point there, definitely not a maximizer. Is everybody cool? So, in particular, the big point I want to make about this is that what we can actually say, what we can deductively reason, is not where maxes are. It's where maxes aren't. Right? This is a process of elimination. Right? What we can actually deduce is simply eliminating contenders, eliminating possible maxes. And it works surprisingly effectively. The points that we can eliminate, here let me go ahead and do this in red. The points that are definitely not maximizers by this reasoning, all of these points along in here, all of these points along in there, all of these points along in here, and all of those points there. Practically all of them. Right? Now, some of the points I can't really eliminate. There are some points that are on the boundary. I can't eliminate those with this reasoning. Does that mean they're maxes? No, of course not. It just means I can't eliminate them. It means ultimately, it means I don't know what's going on at those points. Right? It's not that I know they're maxes. It's that I don't know if they are or aren't. maxes. Likewise, there's a failure of differentiability here. Right, and then let's see here. We have, what would be, I'll use yellow to stand out, where the derivative is 0. Can't eliminate those points. Right, so any point where any one of these things happens, any point that I can't eliminate, we call it a critical point. And this is, I'm going to call it deceptive language. It makes it sound like we've learned something. Makes it sound like we've drawn a conclusion about those points. The right thing to say is that these are the points that we can't conclude anything about. And this critical point label that we put on them is just a label as a reminder to ourselves that we have no idea what's going on. Everybody happy? All right. Okay, so the strategy for multivariable optimization is very, very similar. It's this process of elimination. Like the big picture strategy is still a process of elimination. And here's the process of elimination. Certain conditions being satisfied. If you have a point, let's say this one here, point in your domain. By the way, let's have our domain be this thing like that. So F is defined on that region. So we've got a point in our domain in the interior where the function is differentiable. And what would happen if the gradient were non-zero? And based on how I have this picture drawn here, I think the gradient might be something like, I don't know, I'm going to say something kind of like that, perhaps. In other words, it's increasing. I'm in my mind, I'm seeing it increasing as we're going toward that sort of mountaintop on the right there. So in this scenario, could this point possibly be a maximizer? And I said, no, it couldn't possibly be a maximizer. The function is in the process of increasing. Specifically, it's increasing as I go in the direction indicated by that gradient, which has a direction because it's non-zero. And if the function is increasing, it is definitely not the maximizer we're looking for. Now notice the way I wrote this down. Again, I deliberately wrote this down on the page to look a lot like the way we wrote this down on the page here, because it's morally the same argument, just kind of in a different context. The three-dimensional picture, right? But same basic idea. So again, this works almost everywhere. This does a tremendous amount of heavy lifting for us. This eliminates most of the domain. And all that's left are points where one of these conditions fails, and I guess I don't quite fit this onto one page, so I'll zoom out. There are some points that are on the boundary. If we're talking about points on the boundary, I can't just follow the gradient. I can't, for example, if I were, let's say, at this point here, and let's suppose the gradient looks like it's doing about like that. I can't just go in the direction of the gradient and claim the function's increasing. I'm not allowed to go over there. The function doesn't do anything in that direction. The function's not even defined in that direction, right? So the argument fails. And there's various other examples of the argument failing. Points where the function fails to be differentiable, such as this point right there. Function's not even differentiable there. I can't make arguments about the gradient. Gradient doesn't even make any sense. Function's not even differentiable. Nothing I can conclude. Can't eliminate that point either. And then lastly, points where the gradient is zero. And if the gradient's zero, again, it's not pointing in a direction of the function increasing, because it's not pointing in any direction at all. It's the zero vector. And so that point and that point and that point. So green, blue, and orange, I can't eliminate any of those points. I don't know what's going on at those points. And because of my lack of ability to eliminate those points, I throw up my hands, confess I have no idea what's going on, and I do so by calling them critical points. All right, is everybody good? Now, what do critical points look like? Well, there's a pretty short list of possibilities. If you're in single variable calculus, a critical point might be an inflection point, or it might be a maximum, or it might be a minimum, right? There's a short list of possibilities. In multivariable, there's a lot more possibilities. There's maxes, there's mins. Now look at this one here, though. This point right there, what we call a saddle point for sort of historical reasons, right? Because if you look at the shape, it kind of curves upward in one direction, but it also kind of curves downward in the sort of in the perpendicular direction. And that's what saddles look like. They kind of have to curve downward where your legs sort of hang over, right? But they have to curve upward in front to keep you from flying forward, and to curve upward in the back to keep you from flying off the back of the horse. At this point, it's a pretty outdated reference. Right, I would like to think that in today's day and age, we wouldn't call these saddle points anymore. I would propose we call them Pringle points. Right, it's much more relatable. Right, everyone knows Pringles, but the language is already pretty settled. So you're going to hear saddle point. Okay, but this is not the only possibility. Maxes and saddles are not the only possibility. There's lots of weird-looking possibilities. And just for fun, you'll notice here I have a suggestion here that you should look for something called a monkey saddle. And I've already got that pulled up. And it's instructive in a couple of ways. First of all, that little picture is hilarious. Right? But also, let's look now at, this one's pretty good. So look at the shape of this surface. It's kind of saddle-like in a way, but in some sense there's kind of three downward directions, not two like you would expect in a saddle. We have two sort of downward directions on a saddle because we have two legs. The monkey has two legs and a tail, and there's a better picture of this. Here we go. This one here. You can see the little downward area for the monkey's tail. Isn't that adorable? Right? And then just for fun, I'll point out that if you scroll really far down on this list, I think I remember it's 11 clicks down. Now it's probably, okay, here it is. At some point, somebody put an actual monkey on a little saddle on a horse. I just think that's funny. Anyway, but the surface called the monkey saddle is like this one here and that one there. Now you'll see another funny surface here. This might be a spider saddle, I suppose, right? And the point here is that there are lots of different kinds of surfaces that are qualitatively different from others. Let's see, I saw another one that was worth pointing out. So this one here that we'd been looking at before, notice that in front of the monkey, it's kind of going upward, but behind the monkey, it's just kind of temporarily upward and then it goes down. Well, you could imagine something analogous to that where it's kind of level, more inflection point like on some of the bumps instead of sort of going upward like that. So there's lots of different possibilities. They're all a little bit weird. Okay, so there's that. Is everybody happy? Okay, so let's do one. Here's a function. Let's find all the critical points. Notice this is defined everywhere. The domain is all of R2, which does not have a boundary. So every point is in the interior. So there are no points in this domain that fail to be in the interior. So there's no critical points involving boundaries. Next, this function is differentiable everywhere because it's a polynomial. This is just a fact known, long since established fact about polynomials. They're differentiable everywhere. Notice we're going down over our list here. We didn't find any boundary points, and we haven't found any failures of differentiability. So the only thing left to check is the possibility that there might be some points where the gradient's equal to 0. So no big deal. We take the gradient We set it equal to 0, and we solve to see if we can find any points where the gradient is 0. And this is pretty easy algebra. You can see that whenever x is plus or minus 1, that first coordinate is going to be 0. And then you can also see that wherever y is equal to 0, that second coordinate is going to equal to 0. And between the two of these observations, we can see that these are our critical points right there. Everybody happy? Okay. All right. Now, the algebra on this example that I just started with is unusually convenient. You won't always get that lucky. The algebra of vectors can get a little weird sometimes. And so let me just show you an example. Very often you have to consider what we call cases. The various different possibilities that you need to entertain in order to be able to make any progress in the algebra at all. So, for example, let's suppose this was the little vector algebra system that you wanted to solve, and it's tempting to look at this first equation and conclude that, well, if x squared is equal to y squared, it's tempting to conclude that x must equal to y. But that isn't true, is it? X could equal to y, but equally likely, x could equal to negative y. And we have no reason to believe that case 1 is any more likely than case 2. Everybody comfortable with that statement? Yeah. So, what we have to do here, and before we progress, I have to admit that there are these two possibilities, and I've got to consider them one at a time. First, case 1, we'll consider x equal to y. And then having done that entirely independently, we have to consider case 2 where x could equal to negative y. And the algebra is different for each of these two cases. So, for example, considering case 1 with x equal to y. If x is equal to y, I'll take that and toss it into this second equation. The second equation then becomes this, in which I can solve for y. And once I know y, once I know y, I can also solve for x. So y equals 0 would mean x is equal to 0, which would give me that point. But of course, there is another possibility here, another possibility in this equation. Also possible that y could equal to negative 1. If y is equal to negative 1, then that, going into here, tells me x is also equal to negative 1, and that gives us this critical point. So it's, but again, you got to be sort of careful with how you treat the algebra. Does everybody see what happened there? Okay. All right. Now, all of that was just assuming that x is equal to y. The entirely independent case 2 is, what if x is equal to negative y? Now, everything changes. If x is equal to negative y, we plug that in to there, and this equation becomes that, which is not the same as the algebra directly above it. Right? New algebra, because we're in a new case. And again, then you've got two different possibilities, each of which goes into here, each of which then gives you other critical points. Everybody happy? Now, of course, you'll notice that these two critical points are the same, and so we kind of double counted a critical point. No problem, right? It's still a critical point. Nevertheless, though, we do have 3 critical points, and had we ignored either one of these cases, we would have missed one of those critical points. Everybody good? Okay. All right. So, second derivative test. Y'all remember the single variable second derivative test? The point, there's different ways to think about it. Here's what I like. Here's the second order Taylor polynomial. And if you're considering a critical point where this derivative is equal to 0, this whole term becomes 0. And then whether this value is a minimum or a maximum boils down very simply to whether this second order term is always positive or always negative. This is what it all comes down to. This term might be always positive. It might be always negative. Certainly, you'll notice that 1/2 is always positive. And then we'll also notice that a square is always positive. So what it really comes down to then, the one little, just from the algebraic observation here, the only determining consideration is this right here. That second derivative. Right, whether the second derivative is positive or negative. If it's positive, that means it's concave up. That means you have a minimum. If it's negative, that means it's concave down. It means you got a maximum. Is everybody happy? So I'm going to make a totally analogous argument here to the question of what is the analog of the second order term being always positive. The analog is the multivariable Taylor polynomial second order term. I need to know, when is this always positive and when is this always negative? And again, don't forget, this is a quadratic form. Y'all learned a bunch of stuff about quadratic forms back in Math 218, and y'all will recall, I hope, the terms positive definite, negative definite, and indefinite. Right? And there's also some business about semi-definite. We're not going to worry about that. So 3 different cases: positive definite, negative definite, and indefinite. And what happens to the function, I think, is pretty clear. If this were positive definite, well, then we're looking at a local minimum. Does that make sense to everybody? It's totally analogous to what we just argued in the single variable case. And if this quadratic form were negative definite, then that would mean we have a local maximum, etc. Okay. All right, so then the big question becomes, how do I decide if a quadratic form is positive definite or negative definite or indefinite? And there's a bunch of rules for that, and this isn't Math 218, and I don't want to go off into the weeds, but there is something special to be noted. Let's go back to the formula for the Hessian matrix. Notice that this is a symmetric matrix, right? Because of the fact that the partials, right, we have this theorem that says it doesn't matter which order you take the partials, certain conditions being satisfied. So if this is a symmetric matrix, that actually changes the rules a little bit. It streamlines the process a little bit. And if you'd like to go through and think through the linear algebra, here is an extremely terse sort of set of checkpoints as you go through that reasoning to draw the conclusions that I'm about to show you in what we call the second derivative test. But you don't have to do that. It's not required. It's not expected. It won't be on the test. But just if you're curious, this will guide you through that process. And it's really a pretty cool argument. You can see it gets into diagonalizability and this kind of stuff. So anyway, here's the streamlined punchline, and this is what you do need to know. Second derivative test. You'll notice that we're going to consider only functions of 2 variables. It gets weirder and harder if there's more than 2 variables. Right? But in the case that we have functions of 2 variables, where we're looking at a critical point, right? Here's the nice, relatively streamlined process. It has very strongly to do with the determinant of the Hessian matrix. And again, a bunch of linear algebra here that we don't need to worry about. Roughly speaking, if the determinant is positive, then you're going to get a pretty familiar set of cases. Namely, positive second derivative means local min, negative second derivative means local max. It looks a lot like single variable second derivative test. So how nice, right? That's it's convenient. But I emphasize that only works if your Hessian determinant is positive. 0 is not good enough. It's got to be positive. if the Hessian determinant is negative, let's see here, I'm going to choose a different color. If the Hessian determinant is negative, then it doesn't matter what your individual second partials are. If your Hessian determinant is negative, you got yourself a saddle point of some description. It might be a monkey saddle, it might be a spider saddle, it might be just a regular old saddle. I don't know, but it's not a max, and it's not a min. So, saddle point. Is everybody cool? All right, and then of course the last possibility here that we're going to look at is if the Hessian determinant is 0, and that just means the test fails. This happens sometimes, right? You may recall the single variable second derivative test sometimes fails. It just doesn't, what's happening at that one point just is not enough information to tell the story. And we need more information, and who knows, it could go either way, and we're just going to throw up our hands and say the test fails. So likewise here, you'll notice, by the way, here as well, if in this positive Hessian determinant case, if the fxx is 0, notice I didn't comment there. Test fails there as well. So anyway. Okay, so this is what we've got. Make sure to know these rules. Again, you don't have to know where they came from, but you need to know what those rules are. Here is an example. We previously discussed this function, and we found these two critical points. Now let's figure out what they are. Just knowing that they're critical points. All we've decided so far on these 2 points is that I haven't got the slightest idea what's going on there. So, okay, here we go. Hessian determinant is this. Hessian matrix is that. Hessian determinant is this. And now we'll consider our points, starting with -1, 0. Plug that in. Our Hessian determinant is negative. Which means we have a saddle point. Everybody good? All right, now let's look at the next point. Let's look at B here, 1, 0. Well, you take 1, 0, plug in, see what the Hessian determinant is. The Hessian determinant is positive, which means I have to look more carefully, right? There's these two different sub-cases when the Hessian determinant's positive. It says here that I need to look at fxx. That's the second partial with respect to x. Conveniently, I see it right here. It's the top left entry in the Hessian matrix. And I need to know whether that is positive or negative. So I got to take our point here, still looking at 1, 0. I plug that into there. This second partial with respect to x is positive. That means local min. So we have a local min. What do you think? Everybody see the process? It's very mechanical, right? Plug and chug. So make sure you know what those rules are. See how the plugging in process works. That's the second derivative test. Okay, moving along. We're making great time. I am actually going to skip this next bit. This is not... Oh gosh, let's see how to say this. This is a much longer conversation than what I've written in the notes. And it's kind of a luxury when we have extra time. I like to be able to talk about global extrema, but it doesn't really fit in well, and we don't just have loads of extra time here, so I'm going to skip all this. You're not responsible for it. Ultimately, it's not that big a deal. It's just an observation that under certain conditions, you can conclude that there actually is a global max. And big surprise, the way you find the global max is to collect critical points. Realizing, of course, that any point that you've eliminated, anything that's not a critical point, couldn't possibly be the max. So you just look at all the critical points and check them. It's not a deep idea. There's a tedious calculation here, which I would rather not have to go through. And here's the good news. The question that this tedious calculation addresses, we're going to have a much better technique for this coming up momentarily. So rather than show you a bad method and then you kill a bunch of time with the bad method and then show you the good method that obviates the bad method, let's just go straight to the good. Okay. All right. So Lagrange multipliers, section 4.3. Again, we're making great time. And now this is a subtle subject. Careful points to be dealt with. So this is about optimizing a function, but specifically what we call constrained optimization. So the question will not be, where is this function as big as possible? The question will be, given that I'm only allowed to look at certain points satisfying a certain constraint, among points on the constraint, where is the function as big as possible? And this is a significantly more challenging question. So, for example, let's look at this question right here that says closest to the origin. Okay, closest to the origin. You know what? The origin is the point closest to the origin. That was easy, right? We want to make distance to the origin as small as possible, so we're minimizing, not maximizing, but attempting to just say, well, how about the origin itself? Well, the problem is harder than this. We're not allowed to just entertain any function where f is defined, or excuse me, any point where f is defined. This example asks, among points on this surface, among points satisfying this constraint equation, just among those, you're not allowed to look at any other points. Which of those points is closest to the origin? Right? And so we can't just say, just plug in x equals 0, y equals 0, because x equals 0, y equals 0 doesn't satisfy the constraint. Does everybody see the stickiness on this? Okay. So now there is a wonderful technique for how to deal with this problem, but I want to set everything up a certain way. First, we need to have certain lingo identified, and we need to frame the question in a very specific way. So we're going to define something called the objective function. What we mean by the objective function, it's the function that you want to optimize. In this case, we want to minimize a certain function. Sometimes you want to maximize a function, whatever. Whether you're minimizing or maximizing. The function that you want to make as big or as small as possible. It's called the objective function. And the question says here, closest to the origin, and so I'm going to use x squared plus y squared as our objective function. Now you might complain and say, hey, shouldn't that be a square root? Right? Distance is the square root. So, clever move. I didn't think of this one myself, right? Somebody showed me, I'm showing you. It's a clever idea though. If you find a point that maximizes or minimizes distance squared, that point will also maximize or minimize distance itself. You just kind of think about it. If it's the point that makes distance as small as possible, it also makes distance squared as small as possible. Does that make sense to everybody? I hope that's reasonable, right? And why would I do such a thing? Why wouldn't I just, use distance directly? Well, it's because I don't like square roots. Square roots makes algebra harder, and if I can avoid harder algebra, I'm going to avoid harder algebra. So it's a clever move. Wish I'd thought of it. I encourage you to use this little hack when you have distance-related optimization problems. Okay. All right. So that's what an objective function is. The constraint function. Constraint function is a function whose level set keyword level set. A function whose level set, one of whose level sets, defines what the constraint is. So now, keyword again, level set. Right, so you notice up here in this equation, I've already got it written as a level set. I've got blah, blah, blah equals constant. That means level set. So the function that does this, the function whose level set is my constraint, is this function right here. Is everybody happy? Now, heads up, you got to be careful about this. Sometimes these constraints will come at you like this. It'll be blah, blah, blah equals more blah, blah, blah. Right? So don't make the mistake of thinking, I guess I'll just do, I don't know, I'll pick the left side. Right? No, you can't do that. What you have to do is you have to take your equation and algebraically do whatever is necessary, such as throwing all those terms on the right over to the left, to get it into this format where you have a constant on the right-hand side. Doesn't matter what the constant is, but it's got to be a constant. Yes?
Why is 4 not subtractive?
Yeah, because the only constraint, the only requirement, I should say, is that it be a level set. It doesn't matter which level set it is. So now, just to, well... let's see here. Yeah, let me just say, ultimately, all we're going to need is that it's a level set. And all level sets are just as good. Yeah. Anybody else? Yeah. Oh, yeah. Okay. Yeah. Okay, so this is the setup, and you got to follow these rules when you're setting things up for this particular technique that we're about to apply. We need a unambiguously defined objective function and likewise constraint function. Now, there's something really confusing about this I want to recognize, and y'all need to watch out for, in your own mind, accidentally conflating these two functions. Because it seems like, when you most of the time when you have a question to answer, there's the function, right? This question, there are two functions, right? And both of the functions are really important to the solution. They are different and unrelated functions. So that, again, it kind of makes it a weird category of questions. The issue, again, to be concerned about is that you might accidentally conflate these or swap these, right? Something like that. You can't do that. You got to be really careful. So always be on the lookout. Always be thinking carefully to distinguish the objective function from the constraint function. Okay, a couple more examples. Let's look at this question right here. We want to find what is the biggest box of a given fixed area. Okay, well, the function that we want to optimize, the thing that we want to make as big as possible, is volume. The constraint is that the area is fixed. So my constraint equation is going to say area, whatever my parameters are for my box, that area has to equal to a constant, whatever that given area is. And so area is our constraint function. Everybody on board? Okay, now let's look at this sort of more real world, I don't know, anyways, this is a real world example. I want to maximize my productivity, as a lot of businesses want to do, but I got to recognize I have a limited budget with which to buy materials and hire labor, blah blah blah. Right? So, how would I fit this into our format? Well, my objective, the thing that I want to maximize, productivity. I'm going to need to write down a formula for productivity as a function of whatever my parameters are. Productivity is what I want to maximize. What's my constraint? My constraint is, well, I have a limited budget. My budget is the thing that has to be a fixed constant, because that's what I only have so much of. Does that make sense? Okay. Right. Okay. So, we again have a process of elimination. It's just that now the process of elimination is significantly different, and it's really not all that that's a little analogous to single variable, but there is no single variable analog really. I mean, so this is kind of new territory. So anyway, here's how it works. We keep in mind we are stuck on our constraint set. Right, namely, we have to satisfy our constraint equation. So the only points that we're allowed to entertain are points on this green surface, aka our constraint set. Okay. We have a let's see here. We have our objective function. We have our constraint function. I do need for both of those to be differentiable. Another assumption that I'm going to have to make here, and you'll see why in a couple of seconds, I'm going to need my constraint gradient to be 0. By the way, by the term constraint gradient, I mean the gradient of the constraint function. I think that's pretty reasonable lingo. It's pretty standard. So I need my constraint gradient to be 0. Quick reminder, don't forget, constraint gradients, gradients in general are perpendicular to level sets. So this is a gradient of G, this is a level set of G, and therefore this constraint gradient vector is orthogonal to our constraint set. Yeah? Everybody remember all that from chapter 2, I guess it is. Yeah. All right. Okay. And now let's further assume, keep in mind we've got our constraint gradient like this, non-zero vector pointing perpendicular to the surface. Let's further assume that my objective gradient is not a multiple of the constraint gradient. So if it's not a multiple, that means it can't be anywhere along that line that's defined by the constraint gradient. It's got to point off axis, if you will. Yeah? Okay. All right. So there's our picture. And let's see here. The argument, I claim that if we make these assumptions about this point, then I can eliminate it as a possible maximizer. There's no way that point could possibly be a maximizer that I'm looking for. And I argue as follows. Now, it's tempting to say, hey, what we did in the single variable case is we just said, hey, let's start moving in the direction of that gradient of the objective. Just go in the direction of the gradient. The function's clearly getting bigger, but I'm not allowed to. I am stuck. I am confined to the constraint set, right? I cannot even entertain points that are not on the constraint set. So I can't just go in the direction of the gradient. What I can do is drop a perpendicular, look at, in other words, at a tangent vector that's kind of a projection of that objective gradient. I can go in that direction. I can ask, all right, as I go in that direction, how fast is the function increasing? Directional derivative, of course, gives me that, which we compute by this formula. And looking at our picture, keeping in mind that our objective gradient, let's see here, our objective gradient is this. This says dot it with the direction that we're going, which is that. Looking at our picture, that dot product's clearly positive. Right? Is everybody happy? It's got to be positive because keep in mind, we're off axis, right? There's definitely some angle there. This gradient of f is definitely not pointing perpendicular to the surface, and so therefore the angle between the objective gradient and its shadow has to be an acute angle. That dot product then has to be positive, which means the function's increasing. Whoop! Oh, wrong color. Sorry. Directional derivative is positive. Function's increasing. This point, not a maximizer. Everybody happy? This is the nugget that makes it work. This is the underneath it all why Lagrange multipliers works. Let's finish off the argument, though. Little details. This argument allows us to eliminate most of the points in the domain, most of the points on the constraint set, that is, and what remains, simply the points that I can't eliminate. If either f or g fails to be differentiable, right? If the gradient of g is not 0, in other words, if the gradient of g is 0, if the gradient of f is not parallel to g, in other words, if the gradient of f is a multiple of the gradient of g. So if any one of these three things happens here, our argument fails, right? Any one of these three. Our argument fails. We can't eliminate it. Who knows what's going on at that point? Maybe it's a maximizer. I haven't got the slightest idea. Let's just call it a critical point and we'll deal with it later. Everybody happy? Yeah.
What would it mean if the gradient or the gradient of the level set was 0? Because it's always perpendicular to the level set, but then if it's 0, it's a...
So what it is it's always orthogonal. It doesn't have to be perpendicular. Perpendicular implies non-zero, right? So no, I mean, you're right. It's entirely possible the gradient of g could be 0. If the gradient of g is 0, what that would mean on this picture is just that instead of having that, we would just have the gradient of g would just be kind of the 0 vector down here. And then the point is I can't... this statement here no longer makes any that doesn't help me distinguish between the gradient of f possibly being that versus the gradient of f just being that. And so, again, it means that my argument has failed, and it could go either way. Does that make sense?
Yeah.
Yeah. All right. So we have a new set of criteria to find critical points. So we've gotten it down to strategically kind of analogous, approach to how we did regular optimization. So make sure to know these three conditions. This is what I like to call the differentiability condition. All right. For reasons that won't become clear in this course, but really good reasons, ultimately, we call this the degeneracy condition. Don't worry about why. But anyway, degeneracy is a reasonable description of what happens when the gradient of g is equal to 0. Weird things can happen on the surface, really is kind of the point. And then this is called the Lagrange condition, thus the name Lagrange multipliers, the multiplier being the thing that you multiply by the one gradient to get the other gradient. And the Lagrange condition, now most of the time, this is going to be the one that leads to your actual critical points, but that doesn't matter. Keep in mind, what we have is a process of elimination. If you want to claim that something is, the biggest or the least or whatever, you have to entertain all the possibilities. And the only way you entertain all possibilities is by actually checking all three conditions. So again, it's very important to check all three conditions. If you don't check all three conditions, then you haven't really proved anything about any of the points that you find. So do make sure to check all three conditions, even though in practice, in terms of the answer at the bottom of the page with a box around it, it's probably going to come from this one, not the point, right? Remember, it's not a class about answers, it's a class about ideas, and from an ideas and reasoning point of view, you really do have to check all three. Doesn't matter really where the critical point actually came from. Does that make sense to everybody, I hope? Yeah. Okay, so let's do some examples. Here's a reasonable question. We got a surface S, pretty weird looking surface there, but let's find the highest point on this surface. All right, highest point on this surface. So highest means this is what I want to maximize. That function z is my objective function. That's what I want to make as big as possible, right? Okay. What's my constraint function? Now, be careful. We've got to make sure we're looking at a level set, and conveniently we are here. You see right here, equals constant, equals 4 in this case, but whatever, any constant will do. So that means that this is our constraint function. So we've got an objective function, we've got a constraint function, and now all we have to do is go through the process. We've got to, play the game with these three conditions and see what critical points come up. And here we go. First condition, I need to check differentiability. So looking at these two functions, notice both of these functions are polynomials. Polynomials are differentiable everywhere. All you got to do, just from a strategic standpoint, exam grading standpoint, just say differentiable. You don't even have to spell it out, right? I'll take the abbreviation. But I do need a recognition that you've thought about condition 1 and that both of the functions are differentiable. And if they're not, then you have to recognize where they fail to be differentiable, and you have to label those as critical points. Usually doesn't come up. But I need a doff of the cap to that point of reasoning. So tell me they're differentiable. Is that cool? Now again, this is a glass half full, glass half empty situation. You could take it as, I'm going to get docked points if I don't put that. I suppose you could take that glass half empty view. The glass half full view is, hey, free points. All I got to do is just recognize the differentiability condition and I get free points on a Lagrange problem. Right? So that's what I encourage. Okay, is everybody happy with that? All right. Okay, next. Degeneracy. I need to look for where the gradient of g might be 0. And, okay, well, here's the gradient of g. Let's see here. Let me recover this color. Here's the gradient of g. How am I going to decide where that's equal to 0? Looks like it could get ugly. I think the following is a very convenient take on it, and that is to rewrite it like this. And so now, instead of asking where some vector expression is the 0 vector, we can effectively rewrite it as, I just want to know the set of solutions to this little 3x3 system of equations. And this is straight up Math 218, right? First week of classes, probably. I guess it depends on what order they do the topics. But how do you solve a system of equations? Now, you could row reduce, I suppose. A nice, convenient approach here instead, though, is to observe that the determinant's non-zero. By virtue of the determinant being non-zero, this is a non-singular matrix, which means there's a pivot in every row, pivot in every column, which means we have existence and uniqueness. Obviously, 0 is a solution. Therefore, 0 is the only solution. So we just solved that little system. Those words ring bells? Is everybody happy with all that? Okay. Keep in mind, Math 218 is prerequisite, and this little stuff like this is going to come up here or there. Okay, now, tempting to say we found a critical point, because after all, at that point, the gradient of g is equal to 0. Isn't that what this says? Isn't that degeneracy, or the gradient of g is equal to 0? Keep in mind, all we're doing here is trying to eliminate points that are on the domain. Let me say that differently. We're only interested in points that are on the domain. And this point right here is not on our domain. It's not on our constraint set. So I don't need to eliminate this point. It wasn't a candidate in the first place. So we're not going to label this as a critical point because it's not on our constraint set. Does everybody follow that reasoning there? It's an easy sort of mistake to make. If you call this a critical point, it's pretty wrong. It's not a contender. Okay. Yes?
Wait, why is it not on that side?
Yeah, because it doesn't satisfy that equation, right? You plug in the 0. Yeah, does that make sense?
Yeah.
Yeah, so, boom. Yeah. Yeah, anybody else? All right. Okay, so we had no failures of differentiability. We had no degeneracy issues. And it's therefore down to the Lagrange condition. And here it's just a matter of writing it down. Now, our objective function has this gradient. And so, if you will, the left-hand side of the first 3 equations I've written down there are that objective gradient, 0, 0, 1. And then let's see, our constraint function, all of that jazz. Here's the constraint gradient, and I need those then to be the right-hand side of these 3 equations. And here then is our Lagrange, our trio of Lagrange equations. That's what comes out of this, this is kind of the vector form of the Lagrange equation. So I got those equations right there. Now I also wrote down, you'll notice, let me do this in a different color. I also wrote down this equation right here. Why did I write down that 4th equation? Same point as before. I'm only interested in points that are on our constraint set. I don't have any need to eliminate points that aren't on our constraint set because they're not even on our constraint set. They were never contenders in the first place. So same point. So really what I need, it's not just points that satisfy this purple system. I need points that satisfy the purple system which are allowed in the first place. So effectively then I have this 4 equations. Everybody good? Really easy to forget this part right here. Don't forget to add your constraint in, and when you start solving, you got to have all 4 equations there. And now begins the less mechanical part of the story. How you solve a system of 4 nonlinear. You'll notice. Highly nonlinear set of equations with 4 unknowns. And in general, this is a really hard problem. In many cases, it's just, it's not tractable. You just can't do it. Right? Now this is, mostly a problem for me and not a problem for y'all. It wouldn't be reasonable for me to give y'all a question where the resulting system of equations can't feasibly be solved, right? So this, like I say, is my problem. I have to make questions where the resulting system is doable, right? Y'all just have to be able to solve the doable systems. So all the examples that I have in here are all perfectly doable, but they are all a little different. So I'm going to show you kind of different ways that solving these nonlinear systems might play out. And again, this is just tools for your toolbox. They're all different, right? So here we go. We look at this pair of equations right here, and it's tempting to cancel the lambdas. And then, look at those equaling that. But I can't do that. I cannot cancel the lambdas. Because lambdas could be 0. I'm not allowed to cancel 0. So the very first thing that I have to do is I have to justify my eventual hope to be able to cancel the lambdas. And it comes out of this equation right here. This equation right there actually immediately tells me lambda cannot be 0. Everybody see that? If lambda were 0, that equation would turn into 1 equals 0, which is nonsense. So there's no way lambda is 0. That then allows me to cancel these lambdas. And then A and B turn into these 2 equations right here. Does everybody see that? Okay. Now, this business about worrying about whether or not you're canceling a zero or not canceling a zero, it might seem like sort of, uptight, are we really going to get that careful about this kind of stuff? And yeah, sadly, we really have to. It makes a big difference. I'm going to show you an example in a couple of minutes where it makes all of the difference. It's tremendously important. So please do be careful about this. And if you make illegal algebraic moves by being too fast and loose with canceling things that might be zero, especially on a question like this, it'll probably cost you a little bit, maybe a point or something, right? Not a lot, but it's worth taking a moment to pause and think it through and treat it appropriately. Okay, so there you go. All right, so this pair of equations right here, pretty easy to solve, as it were. I mean, we don't get actual solutions, but we can see relationships between x, y, and z. In particular, this allows me to plug in for x and to plug in for y, and then, of course, obviously elsewhere here as well. And altogether then, that makes this equation turn into that. Everybody good? So this is how, and of course it's all over at this point. All over with the shouting. This is just a bunch of z squared terms that combine like this. You can solve for z. Two possibilities. Each one of these z's, of course, tells you your resulting x's and y's, and depending on whether you're looking at the positive ones or the negative ones, you get these two critical points. Everybody see the sort of the final crumbling of the cookie there? Yeah. Okay. So that's how this one works out. Again, they're all different, and this is just one example. Okay, I'm going to move on to the next one unless anyone has questions. Yeah, go ahead.
You have to plug in the values of z back into your surface.
Oh, well, it depends on what the question asks. Oh, yeah, in this case I really should, right? Because it doesn't say find critical points. It says literally find the highest point. So, yeah, I kind of spiked the football on the 2-yard line here. What I should do is look and see which one of these has the biggest z coordinate, and clearly it's this one. And so this is the point that has, on the surface that's the highest. Yeah. Thank you.
Yeah, I guess also what I was asking is you have to plug it into that surface equation. You can't use any of the other.
Oh, no. We don't have to plug back into the constraint because the constraint was one of the equations I solved.
So you can just use one of the simpler ones to get x.
Oh, yeah. That's right. In this, again, it's every one is different, and no promises that it'll work out so nice. But once you have x and y as functions of z, then yeah, you just plug right in there to get your x and y's. We got lucky in this case. Who knows in general? Yeah. Yep. Anybody else? Okay. All right. Here's another one. So this is the one that we skipped because, well, it was tedious doing it without Lagrange multipliers, and I figured we're going to do it with Lagrange multipliers, so why don't I skip straight to the good method. So here we go. We want to maximize this function on this constraint set, which, again, keep in mind, that means I have my objective function and the function whose level set I'm looking at, and again, very important that this is a level set, right, means that this is my constraint function. Yeah? Okay. Okie dokie. So, there's my functions. I went ahead and took my my gradients because I know that they're going to come up. So, a little bit of algebra. There you go. There's my gradients. Let's go through our process, our three-step, list of 3 conditions to check. Polynomials are always differentiable. Easy. The degeneracy condition. When would this be 0? Well, it absolutely can equal to 0. That's equal to 0 when x is the 0 point. right? Now, should we call this a critical point? After all, it does make the gradient of g equal to 0. But we don't count it because it doesn't satisfy the constraint. In other words, we found a point that's not even on our constraint set in the first. We found an illegal point. So ignore it. It's got nothing to do with the question. Is that cool? Yeah. All right. And now it's a matter of doing the Lagrange equation. So the Lagrange condition turns into this pair of equations. Again, don't forget about your constraint in the first place. Again, we only care about points that either do or don't satisfy the Lagrange conditions if, in fact, they are on the constraint. So again, altogether, what we actually have is this now list of 3 equations. And we only have 3 this time because, of course, there was only 2 variables for our functions. So again, we have a system of equations. Again, the algebra is different every time. The cookie crumbles differently. So tools for your toolbox. Here's the slick move here. I would like to solve for this lambda and for this lambda and argue that because they're both lambda, those 2 solutions must be equal to each other. Wouldn't that be nice? And it's tempting to just sort of, fly forward and do that. But a little subtlety, and again, it is annoying to have to worry about this sort of thing, but it really matters. In order to solve for that first lambda, I would have to divide by x. How do I know x isn't 0? I need to worry about the possibility that x might be 0. You can't go around dividing by things unless you're quite sure that they are not 0. So first thing I have to entertain is x 0. Could x be 0? Could y be 0? And conveniently, you could just directly plug in right here and just immediately see if x is 0. That equation right there just turns into 1 equals 0. That's ridiculous. Therefore, x isn't 0. So no big deal, right? You can easily see that these equations immediately tell you that x and y are non-zero. You gotta say it, right? Again, you gotta write it down. Again, keep in mind it's not about the answer, it's about the argument. It's about the reasoning. And so you gotta give me that little bit of reasoning. Is everybody happy with that? Easy to oops on that, of course. Okay. Alright, with x and y non-zero, then as previously noted, lambda equals lambda, so therefore that equals that, and then you can move those equations around a little bit, and that tells you that x has to equal to negative y. Now again, it doesn't end the story, but we have a relationship between x and y that we can now plug into there. Our constraint equation then becomes this, which is easy to solve. Is everybody good? And once you have your 2 possible values of y, you can plug that into there, and that then gives you, come on, colors, that then gives you your 2 possible values of x. And there's your critical points. Yeah?
Why are there only 2 possible as opposed to 4?
I see what you're saying. So now y has 2 possible values, right? And it is true that x has 2 possible values, but that doesn't mean that all combinations work. So in particular, it says right here, x has to equal to negative y. So think of it as y has 2 possible values, but for any specific possible value of y, there is exactly 1 possible value of x. X then has to be exactly. Yeah. It's a good question. Anybody else? Okay. Oh gosh. Okay. All right. What the last example? Now let me skip over some of the initial stuff that we've done a bunch of times. Objective function, constraint function. We've talked enough about how to identify those. We take the gradients. We worry about whether they're different. Oh, come on, eraser. We worry about whether they're differentiable. That's easy. They're polynomials. We worry about whether there might be a degeneracy. Easy to look at. It's not on the constraint set. That's just like a previous example. I want to talk, though, about how to solve this system. And this is a landmine. And this also shows how extremely important it is to be careful with accidentally dividing by 0. Because it is so tempting. So many students would look at this and say, well, this right here says that lambda has to equal to 1, doesn't it? I mean, come on, it says, right, just cancel the 2x on both sides, and lambda equals 1, but this says lambda equals 1/4, and we're done, because lambda cannot be equal to both 1 and 1/4. Those are different numbers. And it's tempting to therefore say, okay, we're all done here. Contradiction, no solutions, and you drop the pen and walk away. And lose a lot of points because this reasoning doesn't hold water, because we implicitly we're canceling things that might be 0. So now let's treat this properly. The proper treatment is to recognize that, look, I would like to be able to cancel these x's, but to do so, I have to assume that x is non-zero. And I would like to be able to cancel these y's, but to do so, I need to know that y is non-zero, et cetera, et cetera. So what I really have to do is recognize that there's 3 separate cases to consider here. If I want to fiddle with these equations, that is, right? And now I claim this is an exhaustive set of cases. The only point that is not included in one of these cases is the origin, which we've already agreed, not on our constraint set, right? If we were looking at 0, 0, 0, it fails this equation. So every remaining point has to satisfy at least one of these cases, and so all we have to do now is think about the cases. Is everybody cool with that? All right, so let's take these cases one at a time. We'll start with x being non-zero, in which case I cancel and lambda has to equal to 1, which I can then plug in to here and here, and and then these equations tell me y and z are both 0. Right? If lambda is equal to 1, 2y equals 8y, y's got to be 0. Likewise with the z's. And then, when y and z are both 0, that allows me to solve for x. And so you see I actually get 2 critical points out of that first case. 6, 0, 0, and negative 6, 0, 0. Did everybody see how that algebra went down? Okay. So now that was just case 1. Likewise for case 2. Likewise for case 3. And so grand total, in fact, we get 6 critical points. Had we been fast and loose with cancellations and who cares if it's 0, whatever, let's not be too uptight about this, we would have missed 6 critical points. And that would have been, of course, catastrophic for, grading purposes, right? So please do be very careful. Please watch out for your 0 cancellations, lest you miss some big points. Okay, we're done with the course. Enjoyed working with you all, and we have our last exam, of course, on Monday. And see you then. Good luck studying this weekend. Have a good one.